Okay, thank you everyone. My name is Huan. On behalf of our team, I'm glad to present our work called Explainable Defense Coverage Classification in NFL games using deep neural networks. So just a little bit of background on this work. This is a collaboration between Amazon Machine Learning Solutions Lab and NFL Next Gen Stats. At Amazon MLSL, we work backwards from the customer's business problem to identify prioritized ML use cases. And then depending on the use case, we develop ML-based solutions across a diverse spectrum of industries. Of course, we will focus on sports in this presentation. And this is in collaboration with NFL NGS, who captured real-time player tracking data of NFL football games and provide different stats, insights on different aspects of the game. In this collaboration, our objective was to develop the new stat called coverage classification for the football season. So on the agenda, first I will briefly introduce the coverage classification problem, and I'll give a high-level overview of our approach. Next up, I will talk about our quantitative evaluation and model explanation results. In the final, we have the Q&A session. So what is defense coverage classification? The coverage scheme refers to how the defense counters against the offense's passing attack. And for coverage classification, the objective is to identify the deployed defense coverage scheme for a specific play. Suppose we have an example play like this. The right circles represent the offensive players, and the blue circles represent the defensive players. And this is how they line up before the play. And once the play starts, because we have the tracking data of the players, their location, speed, accelerometer, we can visualize them in this way. But the play is usually very short. There's a lot of temporal dynamics happening in the short duration of time. And our objective for coverage classification is exactly to put the play and the defensive strategy into one of the 8 common coverage classes. For example, we have cover 0 man. This is a typical type of man coverage, where each defender is responsible for a specific offensive player, and they tend to follow them throughout the play. Another example is cover 2 zone. This is a type of zone coverage. Instead of responsible for a specific offensive player, the defender is responsible for a specific area on the field. And this is a cover 2 zone because we have 2 deep safeties on the top and 5 zone coverages. So aside from these 2 classes, in total we consider 8 common coverage types, and the objective is to put the defensive strategy into one of the 8 buckets. So what's the motivation? Why do we want to perform coverage classification? So in a lot of existing analytics, the emphasis is on the offensive side of the ball. But at the core of analyzing the defensive, the coverage classification is really important to understand and analyze the defensive strategy. It can reveal how the coaches, the teams adjust their defensive strategy based on the opponent's strengths. It can also help us to develop the defense-oriented analytics. So why we need a machine learning-based solution? If you think about the existing solutions, it's pretty much based on manual analysis. The experts need to look at the visualization of the play, at the same time some actual game footage to really identify the coverage utilized. So this is both laborious, time-consuming, and require a lot of domain knowledge from the experts. A machine learning solution can be enabled by the rich sensor data on the player tracking. And importantly, it can make live defensive coverage possible for the first time. Because the model is really fast for inference, takes just a few seconds to classify the coverage types. So this will enable this coverage classification analytics during the game. And post the game, it can also help us to facilitate a fast analysis by providing the coverage classification results really fast. So throughout this project, we identified mainly two challenges. The first one is on the modeling side. So in order to identify the correct coverage class, there are multitude of information to account for, including how they line up before the play and also a lot of intricate temporal progression once the play starts. Also, we identified there's actually a lot of ambiguity and overlap among the 8 general classes. For some of the play, it's very hard to put them into a specific category, but instead it can be a combination of 2 coverages and even more. And the second challenge is on the model interpretation. So deep learning models usually have better performance, but at the same time, they are very opaque. It's hard to understand the internal working mechanism. And model interpretation are very necessary to ensure that the model can capture the correct football signals and also identify problematic instances that should be routed for manual review. So next I will talk about our general approach to this problem. As the input, we have the player tracking data and the manually annotated coverage labels. The first step is feature engineering. We follow some existing work on this domain to construct the relative feature, for example, relative location, speed, acceleration between each pair of the players. So that's how we arrive at the features at each frame of the play. Once we have these features, we put them through a convolutional neural network to model the player interactions and arrive at the frame embedding. And on top of that, we just stack a self-attention module, the same module utilized in the transformer, to compute the play embedding that can represent the entire play. And with that, we can simply stack a linear layer to classify the final coverage class. So these neural network modules constitute our CNN attention model. At the same time, we find it's beneficial to develop multiple CNN attention models and do a model ensemble to derive the final coverage classification result. And to support the interpretation, we develop a global explanation that can perform a coverage discovery on a global scale, and instance explanation that can zoom into a specific play and extract interaction highlights. Now let's look at some results. We first perform a quantitative evaluation utilizing 4 seasons. We utilize the first 3 seasons for training, validation, and the 2021 season for testing. So here's the evaluation results. We compare with a baseline called Zoom model. This is the model derived from one of the previous Big Data Bowl Kaggle competition winning solution. So this model utilized the same feature engineering as we do, but it focused only on the first frame of the play to infer the coverage class. We also compare with different variants of our model, including a CNN-LSTM model and a single CNN attention model without the ensemble and some of the other training components. So we have 2 observations. The first one is that our model outperformed both the baseline and different variants. This demonstrates the effectiveness of the proposed components. And very interestingly, if we compare the test 1 accuracy of the 8 coverages and the top 2 accuracy, we see a large gap here. This means that if the top prediction from the model is wrong, the second guess is mostly correct. So this is something we found it related to the coverage ambiguity. Sometimes it's just really hard to assign a single label to the play. Instead, it can be a combination of multiple coverages. So to understand that more, we perform the model interpretation. And I first show a global explanation result For the global explanation, this is analysis of the learned play embeddings. We utilize the t-SNE visualization. Each dot here represents a play, and the color of it represents the ground truth coverage label. The general observation is that the different coverage classes, they are pretty well separated. This demonstrates that the model learns to classify the correct coverage class. But at the same time, there are some very interesting observations we see from the visualization. As an example, we see some overlapping regions among the coverages. For example, if we extract this cover 3 zone and cover 1 man, which are the green and blue coverage classes, it's clear that now the overlapping part is this red region. We utilize the algorithm to extract this specific overlapping region, and we sample some example plays on this region for manual review. And the results turns out that most of the plays in this region, they have adjustments that looks like a mixture of zone and man coverage. Remember that for cover 1 man versus cover 3 zone, they are quite similar. And the main difference is on the leftmost and rightmost cornerback. Are they in man coverage or zone coverage? But for this example play, this overlapping region, we identify that the cornerback on one side is locked into man everywhere he goes, and the other cornerback has more traditional zone drop. So this combination explains that the model's confusion. So next, we zoom into the individual play. We develop instance explanation method. I won't go into the details, but we utilize a guided grand CAM algorithm to extract the most important image pixels from the feature engineering, and then we project back from this pixel into the football field to highlight the player interaction. If there's a strong signal of the player interaction, we will draw a thick line between the players. So I will show one example of the instance explanation results. It's quite useful to explain the ambiguous classes. For example, for a specific play, the model returns 62% of cover 1 man and 28% of cover 0 man. We first utilize the instance explanation to let the model explain the cover 1 man classification. As shown in this snapshot of the play, the important signal discovered by the model is on the interaction between the wide receiver and the cornerback. So this is a clear indicator of the man coverage. But at the same time, if we ask the model to explain cover 0 man, which also have a relatively high probability, these are the signal recovered by the model. I will highlight 2 parts. This play actually is what we call play action fake. The quarterback will will fake a handoff to the running back before passing the ball to the other players. And the model is kind of able to discover that as the attention received on the running back. At the same time, there's a strong interaction between the wide receiver and the strong safety. This is the main indicator of the model's confusion to classify this play into a cover 0 man coverage. And from a general standpoint of view, this play actually happens very close to the goal line. So there's not enough room for the model to identify the deep safety of the strong safety player here. So in conclusion, we developed a novel coverage classification model utilizing ensemble CNN model to identify the coverage accurately, also significantly outperforming existing approaches. And we provide model explanation that explains the model's decision both on the global level and also on the instance level. In the future work, we plan to investigate temporal graph neural network to better model player interactions, at the same time to utilize some game theoretical approaches for model explanation. That concludes my talk. Thank you for your attention.
Great, thanks very much. Super impressive. So my question is going to, I think, focus on that. when you compared your results to, you said there was a Kaggle competition where others had tried in the past. So compared to the Kaggle results, your results look terrific. Why? So that's the question. So I guess if you were going to give advice to someone who wanted to build something like this, what were the things that you needed to do to get that much of an improvement over the previous folks who tried the Kaggle competition?
Yeah, so I should explain it more clearly. Actually, the coverage classification has never been done in the previous Kaggle competition, but the solution was actually adopted from the Kaggle competition on another task. And that one is based on the per frame analysis. So because of the success of the feature engineering and so on, we utilize the same model and adopt it for the coverage classification task. Yeah.
I see. And this one's a little bit more of a general question. Do you know, like, I assume the teams are already doing this, that there's somebody on the sideline saying that was a zone 2, that was a man 1, or something. So they probably have this data. So presumably the NFL has some interest in making this data more widely available or making it available for broadcast? Like, where does this go next? Like, if you could do this perfectly, what happens then?
So for the current solution, it has already been integrated into the NFL's system. Mm-hmm. It's able to provide the live coverage classification result to provide to the broadcasters, mm-hmm. to the fans during the game, and also help them with analysis of the game analytics. Mm-hmm. So I'm not entirely sure about the data availability, especially the coverage labels. Mm-hmm. But I think this is something that we can figure out together. Yeah.
Thanks.
I think it flashed very quickly as a kind of conclusion, but I think at some point you talk about creating or identifying new strategies. And so I was curious to your thoughts. You have a few years, I think, from 2018 of seasons of data. How do you see these strategies changing over time? And do you imagine that they're going to continue to evolve with new strategies emerging, new classes of strategies emerging moving forward from this type of work?
Yeah, I think there are two aspects of these coverage strategies. First of all, we, as shown on this slide, we identified, initially we just utilized the 8 common coverage strategies to do the classification. But as we build the model, train the model, and analyze the results, there are actually more beyond that. There are some overlap between them that can be separated out into a new coverage strategy. So this is one potential future direction, to do more manual annotation to confirm this new coverage class and potentially supply the labels into model retraining to identify, to infer new coverage classes. And probably another aspect is that we did observe that over time, there's a trend of increase on the zone coverages. So this is what we see in the historical data. But moving forward, we do observe there's going to be some change, some further evolvement of the coverage strategies. And I think it's necessary to have the new labels, probably from the model's inference results combined with human in the loop of verification. But with this new label, it's necessary to train the model periodically to adapt to this change.
Okay, great. And then my final question, if you go back to your results, you talk about the top 2 classified categories being very highly scored. Okay, beautiful. So the top 2, your accuracy there is much higher than the 1.
Yeah.
How are you thinking about trying to change something in your model to try and address that, try and be sharper in your analysis and try and come up with the top classified category more accurately? Is there anything that you can do there in terms of either your objective or something along the lines to improve on that?
Yeah, I think it's definitely worth investigating additional modeling strategies, for example, utilizing a graph neural network that can possibly improve the coverage classification results. But at the same time, I think it's also quite important to analyze this coverage ambiguity, because from some of the feedback we receive from the analyst experts, some of these plays in the evaluation results, it's just, even for them, it's very hard to categorize into one of the specific coverage class. So it means that even it's very hard to say the model is not correct. Yeah, so there's something that's
Yeah, I was going to mention that myself because I've done this project, and you're in my wheelhouse here. I'd love to see it though. A couple things is, yeah, definitely you can show kind of ambiguous coverages to experts and coaches, and you can show them like to 5 different coaches, you get 5 different answers sometimes.
Yeah,
and it's understandable because defenses are trying to disguise what they're actually doing. Also to piggyback. If you go to the slide where you have the instance explanation between like cover 0, cover 1. So one of our approaches, I think this will get you well over 90%, is we do a model like this, then we bolt on top a set of rules that identify like obvious sort of situations. And they don't solve all the problems, but they'll heal. So for example, you have this, high safety who's not close to anybody, and you just have a set of dumb logic rules, like how close is he to the nearest receiver? Is he racing towards, the pass rush? Is he backpedaling? Things like that, and then oh no, okay. So if I have a tweener between cover 1 and cover 0, I can break the tie. So I think that would be helpful. So question about, so you do the clustering. I think that's pretty novel, and that helps you identify these situations, these tweener situations where you could have error. But why is that better than just say identifying the plays with like non-confident classification probability distributions?
So I think they are just different perspective to analyze this ambiguity. So for the cluster analysis, it's more focusing on the global level. What's the general model behavior in classifying the different classes? But there's also a lot of value when we analyze the predicted probability. For example, it might be worthwhile to well-calibrate the model. Well-calibrated model, for example, it returns the 90% of probability, then 90% of the prediction results should be correct. So this is another perspective to, I think, to really calibrate the model and to really determine when we should route this classification result for manual review.
Okay, thanks.
They already asked really good questions, but good job. And I think the thoughtfulness about how to treat these classifications. Are there ambiguous classifications? Are there new classifications? I thought that was really thoughtful. One question I do have is, did you look at like data that isn't about the actual lineup, like down distance score and things like that? Did that help? If you didn't look at it, why not?
Yeah, we actually look like that in the process when we try to improve the model, but it turns out didn't improve in the model's performance in a significant way. So our conjecture was that a lot of this information has already been, the contextual information has already been incorporated into the tracking data, so it doesn't provide some additional information.
Even for like goal line stuff?
Yeah,
is that like
yeah, pretty much, yeah. Thank you for the comments.